Cybertruck engineering truly is next level. Everything in the engineering of Cybertruck is based on first principles thinking, ease of manufacturing, and deletion of parts and processes. So whether you're a Cybertruck fan or just love nerding off on engineering, prepare to be amazed. I know I was. Hey guys, welcome to Connecting the Dots, the podcast where we follow the breadcrumbs and try to predict where disruptions will take us. A short while ago, I posted a video where I connected the dots on which undiscussed features and technologies we can expect Cybertruck to have. The video showed things like unique AI-controlled brakes, steer-by-wire, and many other advanced technologies and features, most of which weren't discussed elsewhere. It analyzed the physics of why Rivian can't do tank turns and showed how Cybertruck should get a unique diamond mode, which unlike Rivian, will enable it to easily do them. And mostly, it showed why adding all these unique features does not add to the cost of building Cybertruck. In fact, it further simplifies its already ridiculously simple production cost, reduces required factory floor space, and lowers the cost of making the truck to levels that other EV truck makers can't even dream of achieving. If you haven't watched the video, there's a link in the card above and in the video description. In this video, I'll enhance the picture by providing an engineering analysis of less discussed, but utterly brilliant, engineering features of Cybertruck's exoskeleton. If you're watching this, I'm sure you already watched hundreds of Cybertruck videos, so I won't waste your time, and mine, repeating for the millionth time how great it is that Cybertruck doesn't need a paint shop, or how the exoskeleton gets rid of half the body shop and costs less to make. You already know these. So instead, I'll provide my own engineering analysis of some things you possibly know and others you probably don't. We'll discuss things like how going from first principles, Tesla removed several levels of dead weight. We'll compare Cybertruck's torsional and lateral rigidity to those of other truck designs. We'll discuss Tesla's engineering wizardry and a whole lot more. I'm sure you're tired of false claims and clickbait videos, so to back these points, let me add that originally, I'm an aerospace engineer, majoring in structures and manufacturing. I have extensive experience in aerodynamic design and analysis. I did highly advanced research, anticipating relevant technologies decades ahead. I've led the engineering of major software-based systems, some of which are world-renowned, and I excel in systems engineering. Everything in this video is my own take on the engineering genius of Cybertruck's exoskeleton. I'll focus on less discussed topics, but even there's a lot to show because Cybertruck engineering truly is next level. Everything in the engineering of Cybertruck is based on first principles thinking, ease of manufacturing, and deletion of parts and processes. So whether you're a Cybertruck fan or just love nerding off on engineering, prepare to be amazed. I know I was. Nothing here is investment advice. I am long and bullish Tesla stock, and I value your time, so timestamps are provided. A special thank you to my Patreon supporters and YouTube members. Those are the people who make this channel possible. If you want to support the channel, there are links in the video description. And if you enjoy my videos, please hit the like and subscribe buttons so I can grow the channel. YouTube's algorithm loves it when there are likes early on, so this helps the video reach more people. Now let's buckle up and get ready, because Cybertruck brings huge disruption, and disruption is never boring.
It won't be boring.
A structural battery analogy. I planned on starting with its unique shape, but with Cybertruck, everything is interconnected. So first, let's start with a short primer on body-on-frame versus exoskeleton design. Chances are you already know that most trucks are body-on-frame, most cars and a few trucks are unibody, and that Cybertruck has an exoskeleton. So to highlight the genius of exoskeleton engineering, I will start with an analogy to Tesla's structural battery. A body-on-frame design is constructed in two parts: a sturdy frame which handles all the loads and carries everything else, including the second part, a body which is attached or suspended from it. By comparison, unified body, or unibody designs, have the chassis and body of the vehicle assembled as a single unit, which carries the load together. Cars moved to unibody construction in the mid-1930s and never looked back, as unibodies are safer, lighter, and cheaper to build. If you want to know why they're all that, watch either Sandy Munro's or Engineering Explains videos. URLs of both appear on screen, but a cool way to understand it is through examples. Imagine there's a 22-pound or 10-kilogram chair, and two guys need to carry it from one building to the next. Now let's select which guys are required to do the job. In this picture, we have two bodybuilders. Can they carry the chair? Of course they can, but that's overkill because even the two nerds in this picture can easily do the job. Now let's imagine one of these nerds is sitting on the chair. Can the other guy carry him all by himself? Of course not. And in this case, we need to get the bodybuilder. What this shows us is that if one component carries all others, it needs to be beefier and much stronger than if more components share the load between them. So sharing the load reduces cost and overall weight. This idea of sharing loads and each part serving more than one purpose stands behind Tesla's structural pack. Most Teslas just carry the battery pack as dead weight, but the newer design of Austin and Berlin Model Ys uses the pack as part of the structure. This enables to spread loads and remove bolstering and makes the cars lighter and cheaper to build. Taking this to body-on-frame versus unibody tells the same story. Similar to how a regular Model Y carries its battery as dead weight, in body-on-frame designs, the frame carries the body as dead weight. And similar to how Austin and Berlin Model Ys use their batteries as part of the structure and have the pack carry some of the loads, unibody designs use the body as part of the structure, and it too takes part in carrying loads. Cybertruck's exoskeleton-based design is like a unibody, in that the upper body is integrated with the lower skateboard and shares the loads. But it doesn't end there. Tesla's first principles approach to engineering raises the question: if unibody removes dead weight from body on frame, is there any dead weight left on unibody to be removed? The answer is yes, because despite having the bottom and upper parts of the chassis integrated, unibody designs still carry their sheet metal as dead weight that does not take any loads. So in typical Tesla engineering manner, Cybertruck's exoskeleton takes a huge step forward and removes even that final dead weight. The best part is no part, and the best chassis is no chassis. So Cybertruck uses the sheet metal itself as the load-carrying chassis, which saves weight and adds performance, economy, and range. Structural, battery, pack. As I said, this sharing of loads is the smaller part of why the exoskeleton is so efficient. But before going on, we mentioned the structural battery pack, so here's a side note. Listen carefully to the following two sentences and try to think how they fit together. Sentence 1. In my opinion, Tesla's inventing the structural battery pack was pure genius. And sentence 2. Sandy Munro was extremely disappointed when he tore down the original Model 3 and found out that it carried its battery pack as deadweight, while other EVs, such as the 2018 Jaguar I-Pace, had a structural battery pack. Feel free to pause the video for a moment to think this over, because the first sentence says that Tesla invented the structural battery pack, while the second says that other cars used it long before. So what gives? Think about it for a moment. The answer is that structural is followed by both battery and pack, and it all boils down to which of these words structural refers to. Tesla isn't the first company to realize that it's inefficient to just carry parts without having them carry some of the loads. All legacy OEMs learned this long before Tesla was formed, and so it was only natural for Jaguar, as well as other companies, to use the battery pack as a load-carrying part of the structure. So the second sentence is true. The Jaguar I-Pace has a battery pack that is structural, and when doing Model 3, Tesla was still inexperienced in manufacturing, so did not do this, much to Sandy's dismay. Tesla's rate of innovation is like no other company, and whether Tesla took Sandy's comments to heart or they arrived at these conclusions themselves, once they realized they could do better, they set out to fix their mistake. But Tesla doesn't work by analogy, so their first principles approach to engineering raise the question. If using the battery pack as part of the structure removes deadweight, is there any deadweight to be removed from the battery pack itself? Here too, the answer is yes, because the battery pack carries its battery cells as deadweight, and the cells carry battery materials that way too. So Tesla's huge invention with the structural battery pack isn't that the pack is part of the structure, but that so is each of the 4680 battery cells within it. In other words, 4680 Model Ys have everything in the pack carrying loads and no deadweight, which enables the pack's upper and lower panels to be much thinner and lighter. Tesla's 4680 battery pack is in fact a structural battery cell structural battery pack, and from an engineer's point of view, things don't get any purer than that. And in case you wondered, the 2170 battery pack used in Berlin and Austin Model Ys is also structural, but its cells are not. Keep it simple, stupid. I said that sharing of loads was the smaller one of exoskeleton's advantages over body-on-frame, but before getting to the main advantage, let's check for a moment why despite unibody's advantages, most trucks, including new ones like the Rivian RT and the Ford F-150 Lightning, still use body-on-frame. Trucks need to handle a much wider variety of loads than cars do. They need to be luxury cars, providing a supple ride for driver and possibly family. But they also need to be ultra tough and enable hauling a cab full of passengers with a ton of bricks in the bed. They need to be capable of towing huge loads uphill and downhill. They can have cheap rear-wheel drive versions, but also powerful all-wheel drive versions, possibly jacked up and capable off-road. Making a unibody that can withstand such loads takes a lot of analysis work, but what's worse, trucks often have many different versions. Designing unibodies for all versions would take lots of work and result in very different bodies and production lines. But if bodies are just carried by a standalone load-carrying frame without being part of it, this enables changing versions very easy. You want a truck? Attach a cab at the front and a bed behind it. You want an SUV? Just make an SUV body and attach it to the same frame. Short bed? Long bed? Flat bed? No problem. Just replace whatever the frame carries, and since you're using the same chassis, you don't have to analyze your structure from the ground up every time you do so. OEMs usually try to cover every market, so they need to go body on frame. But Tesla is different. They like keeping things simple. Where OEMs have dozens of sedans spanning several sub-brands, Tesla has one small sedan and one large one. That's it. And where OEMs have dozens of SUVs spanning several sub-brands, Tesla has one small SUV and one large one, and both clobber their competition. Similarly, when doing full-size trucks, Tesla chose to focus on making a single design that fits most of the market, not all of it. For example, they're perfectly fine leaving the flatbed market wide open for other manufacturers, when it's just a small percent of the overall market. Foregoing markets also means foregoing their specific requirements and constraints, and simplifying like this removes roadblocks and enables Tesla to build a single model that will absolutely dominate each of the other categories. Torsional rigidity. Going for a single body style enabled Tesla to ditch body on frame and go unibody, or as they chose, an exoskeleton. We already showed that this enables making the body lighter through sharing of loads, and this brings us to the main advantage Tesla's design has, which is rigidity. This section is engineering oriented, and I'll go into equations, but if you're not engineering inclined, don't fret. Just ignore the formulas and I'll make it extra simple without them. There are two types of rigidity, torsional and lateral. Starting with torsional, consider the extreme condition this truck endures, and you'll see the frame endures a whole lot of twisting. Torsional rigidity is defined as how much the truck's structure can resist such twisting. Think of wringing out a washcloth versus trying to twist a metal bar. Not all trucks go rock climbing, but just climbing a curb with one wheel when the bed is fully loaded can introduce a whole lot of twisting moment that trucks endure. To see how they do it, let's check the equations and see what they tell us. This is the equation for torsional rigidity. Torsional rigidity is the product of G and J, where G is the shear modulus and J is the polar moment of inertia. G, the shear modulus, is a property of the material that is used. For example, aluminum is softer than steel, so the shear modulus of aluminum alloys is around 27, while that of high-strength steel is higher, at around 79. Since body on frame, unibody, and exoskeleton can all use some sort of high-strength steel, let's say they're all equal on G. But J, the polar moment of inertia, is where all the fun is. J is a property of frame design, so let's compare all three to each other. To demonstrate this, let's simplify the frame and consider it as a closed box. The polar moment of inertia of box sections is found through the following equation. Note that T is the wall thickness. A and B are the width and height of the box, and the larger A and B are, the more torsional rigidity the frame has. To understand why this happens, imagine that a twisting moment is applied to the truck and every molecule in the frame has to resist it. The farther away the molecule is from the center line of the box, the larger the lever it has, which means less force is needed to resist the twisting moment. Now let's consider the frame of a body-on-frame truck versus a unibody chassis. Looking at the truck's planform view, which means from above, we see that the unibody chassis is wider than a body-on-frame's frame. This means that a body-on-frame's A dimension is smaller, so for the same thickness, body-on-frame should have a lower polar moment of inertia than unibody. Viewing the truck from behind shows a more significant difference. We see that B, the height of the frame, is significantly larger for unibody than for body-on-frame. Since the frame on body-on-frame trucks is small and low, it has to be extremely beefy and heavy to achieve the required rigidity. You only need to look at this picture of the 2008 Ford Expedition's frame to see what big-ass bolstering looks like. And since unibody trucks use the much larger box of the body as a load-carrying part of the chassis, much less bolstering is required to make the truck rigid. The chassis can be much thinner, which results in significant weight saving, higher fuel economy, and in an EV, notably extended range. Look at this picture of the Honda Ridgeline subframe, which is the bottom part of its unibody, and you'll see it's much thinner than an F-150's frame. This subframe alone cannot withstand significant forces and moments without first being mated to the upper part of the unibody, the top hat. But here too, Tesla employed first principles thinking and asked, if width and height increase rigidity, what is the widest and tallest chassis that can be fitted within the truck's given dimensions? The answer was to make an exoskeleton from the exterior skin of the car, which by definition is wider and taller than any chassis that could fit within the skin's outline. This enables all molecules of the exoskeleton to have the largest lever possible, with which to resist twisting forces, and provides a more rigid and lighter chassis than in any of the other designs. It should be noted that to save weight, some body-on-frame trucks don't beef up their frame to a level that's nearly rigid enough to handle expected loads. Instead, they accept frame flex as part of their design, and leave a gap between the bed and the cab to enable each to move a different way as the frame flexes. To me, this seems like giving up on rigidity, and saying that they can't have a truck that's rigid enough for its loads without being overly heavy. Tesla, apparently, shows that anything within the laws of physics is indeed possible with smart enough engineering. The exoskeleton truly is a revelation when it comes to torsional rigidity. So let's move to the other type of rigidity, which is lateral. Lateral rigidity. If torsional rigidity is the frame's resistance against twisting, lateral rigidity, or lateral stiffness, is its resistance against bending. Bending can occur side to side, such as when the right wheels of a loaded truck are on the sidewalk and the left are on the road, or it could happen front to rear, such as when dropping heavy payload into the bed. Just like with torsional rigidity, lateral rigidity is a function of the material used, and the width, height, and shape of the structure. And since all designs use steel with more or less the same properties, it's mostly a matter of dimensions and shape. Instead of equations, let's illustrate this with an example. Imagine you find a long piece of cardboard that is folded and taped to form a long but thin box that is 3 feet long but only 1 inch wide and half an inch tall. Now imagine trying to bend it against your knee. Easy, right? Now imagine you find another box made from the same kind of cardboard, and this box is also 3 feet long, but 1 foot wide and 1 foot tall. Bending this box would be much tougher, right? Applying this to trucks, an old-style truck's frame is very much like that small box, while unibody is more like the bigger box, so it improves on that. An exoskeleton improves on unibody to the absolute extreme. Just like we saw for torsional rigidity, you can't get a larger chassis than that within the truck's outline. Cybertruck. The exoskeleton's larger dimensions can make the chassis stiffer and lighter than comparable body-on-frame or unibody trucks. But the genius goes far beyond dimensions, because there is also that shape. While watching the Cybertruck reveal back in 2019, once the smoke faded away and the truck's shape was clear, I literally jumped out of my seat. They've made a truss! A Cybertruck! You know how some people like the design from the start, while others took time to warm up to it? With me, my mind was blown out by the sheer balls that Elon and Tesla had to show such a pure design. Pretty or not, I didn't care, because with my roots in aerospace structure engineering, nothing could spell to me form follows function more than that wild, triangular shape, the shape of a truss. A truss is a structure assembled from members such as beams, which are connected at their ends by pin joints to form together a rigid structure. The Cybertruck's triangular shape is similar to the most basic truss shape, which is used in construction of bridges, old race cars, and planes. The main idea is that while any member of the truss is light and weak and can easily be bent if alone, joining it to the other members enables passing almost any loads it encounters to the others as compression or tension forces, which are easier to handle. Let's look at a body-on-frame design from the side and imagine a fully loaded truck's front wheels hit a bump on the road. This translates into a vertical force F1 that pushes the front of the frame upwards and creates a moment M1 acting to bend the frame. Now let's turn the frame into a triangle and see what happens. If you're not technical, don't worry about the equations, as I'll be brief, and I'll give a simpler explanation immediately after. We see that if F1 moves the front up, this also pushes the front upper beam up. Breaking this force into components, most of the force is spread as compression force F2C along the beam, and when it reaches the end of the beam, it acts on the rearward beam 2. Breaking this force into components again, a compression force F3C runs through the rear beam, and when it reaches the end of the beam, it acts on the bottom beam. Breaking this force into components again, a tensile force Ft runs through the bottom beam. I highly doubt that Tesla connected Cybertruck's structure with pin joints, so it's not purely a truss, but regardless, the method of operation is about the same. Cybertruck's triangular structure enables distributing of forces operating on the truck along its entire frame, so the entire frame moves together and resists such forces instead of letting a single part suffer it alone. You're probably tired of hearing this by now, but spreading forces over the entire exoskeleton chassis enables making the structure more rigid and much lighter, which improves performance, economy, and range compared to body-on-frame or unibody trucks. Dem Buttresses. Buttresses, or flying buttresses, is the automotive term used for the triangular shapes sloping from the rear window along both sides of the bed. Truck guys often bring them up as a major Cybertruck drawback, saying that they prevent using it as a work truck, since they prevent picking stuff from the bed. I'll show a surprising trick regarding this in the buttress magic part, so don't go away. But first, let's show what the buttresses are about from an engineering viewpoint. Buttress is a term taken from architecture for supports to stabilize a wall. Regular buttresses are built from the wall to the ground or structure below it, and flying buttresses are arches which support the wall by passing the loads to the ground or structure nearby. In cars, both terms are used for the same thing, which is when the rear C-pillar stretches back beyond the rear window. For example, consider this beautiful 2006 Ferrari GTB, the muscular C3 Chevrolet Corvette Stingray, or this graceful 1976 Jaguar XJS. Cars mostly use buttresses as an aerodynamic aid to stabilize the airflow at a notably turbulent point of the body. Cybertruck, however, uses buttresses for both aerodynamics and structural reasons. Let's handle the aerodynamics first. Buttress aerodynamics. Right after Cybertruck was revealed, the Boats and Engines YouTube channel calculated that with the vault cover closed, Cybertruck's drag coefficient isn't extremely low for a truck, 0.39, and Elon tweeted that with some massaging, it could even reach an amazing 0.3. For comparison, they calculated that the 2019 Dodge Ram had a CD of 0.59 and the Ford F-150 0.56, both much higher. However, Cybertruck's drag coefficient should be extremely low, even with the vault door open, as the buttresses prevent air from the high-pressure sides of the car from entering the low-pressure area above the bed. Air will enter the open bed area from the top, but with the steep angle of the windscreen acting like a spoiler, this is easier to manage. Air from the sides can gradually join the fun as the buttresses slope, but the fact remains that buttresses significantly reduce drag. And you guessed it, this improves performance, economy, and range. Structural buttresses. Besides playing an important role in aerodynamics, Cybertruck's buttresses also play an important part in increasing body rigidity around the bed. Remember how when discussing torsional rigidity, we showed that the frame height B plays a major role? And while the frame of regular trucks is very short in height, unibody trucks' frames go as high as the roof, which enables using a much thinner frame to get similar rigidity. All this is great in the cab area, but going back to the bed, there's no roof at all, and all that we have is an open frame that's thinner and not rigid enough. This reason alone is enough for dismissing unibody trucks as not tough enough for work duty, towing, and heavy off-road use. To somewhat overcome this, unibody trucks like this Hyundai Santa Cruz or the first-generation Honda Ridgeline use buttresses. The buttresses move loads to the sides of the body and the upper chassis above the cab, which makes the open bed area a bit more like the cab area and stiffens it. This is extremely important in towing. Body-on-frame trucks excel in towing because the entire towing load is passed as a tension force along the beefy frame. In unibody trucks, most of the towing load is similarly borne by the lower part of the frame. But since this subframe is thinner than a body-on-frame truck's frame, it isn't strong enough to tow large loads without getting torn apart, unless special bolstering is added for towing. Like both other types, Cybertruck too carries towing loads as a tensile force through the lower part of the frame. Unlike others, however, the triangular truss shape passes the tensile loads to the upper beams as well, with the entire structure taking part in handling the load. As a result, Cybertruck can tow heavier loads than the toughest of its body-on-frame rivals, while unibody trucks aren't even in the same zip code. Buttress magic. Buttresses provide structural and aerodynamic benefits, but truck guys usually hate them. The main argument is that buttresses make it hard to reach over the side of the bed, so you always have to climb into the bed to get tools and other stuff carried inside, where in the F-150 you just reach in over the side. As a car guy and a Tesla guy, I've been involved in many debates where Tesla skeptics, not just haters, raised this as proof that Cybertruck might be fine as a lifestyle vehicle, but it's not cut out for work duty. And if you think otherwise, you've never used a truck for work. That's all into discussion. Looking at this direct comparison between Cybertruck and Ford F-150, it's very clear that they do have a point. The sides of the red F-150 in the background are pretty hard to reach over as it is, and it's clear that Cybertruck's buttresses make reaching into the bed almost impossible, except for a small region in the back. With other car companies, this could be a problem, but for Tesla and Elon, it's just another hold my beer moment. And lowering Cybertruck's air suspension by half its travel completely changes the picture. Except for a few inches at the front, it's actually easier to reach over the side of Cybertruck's bed than it is the F-150. Engineering is the art of solving problems, and to me, this is just another example that Tesla's engineering is pure magic. Tell me in the comments below if you agree. The next question. Another place where Tesla removed dead weight is by making the glass structural, but I'll describe this separately when I discuss the glass. To summarize exoskeleton, Tesla's first principles approach achieves extremely pure results. Other manufacturers have battery packs that are load-bearing parts of the structure, but with Tesla, even the cells are structural. And unibody cars have load-bearing bodies, but with Tesla, even that outer skin is structural. And most OEMs make products that can be changed for all niches, but Tesla simplifies by ditching any niches which prohibit making a single superb product that can clobber most of the market as is. Since torsional rigidity increases with cross-section, Tesla increases the cross-section to the theoretical maximum by making it 100% of the truck's external shape. And for lateral rigidity, Tesla employs a pure truss shape. Where other trucks give up on rigidity when asked to carry heavy loads or work off-road, Cybertruck hauls more and goes tough with an extremely rigid but light chassis. Cybertruck's buttresses improve rigidity and aerodynamics. And they have downsides, but Tesla removes them by lowering the suspension when needed. I have never seen a design as pure and as maximalistic in its approach as the Cybertruck. I am definitely awed, and I haven't even touched manufacturing aspects and other topics such as structural glass or how Cybertruck could revolutionize intercomponent communications. I planned on adding them here, but exoskeleton alone held more than expected, so I'll close things now and leave the rest for another video. Since that would be my final Cybertruck video, let me know in the comments below if there are any topics you want me to cover or questions you want me to try and answer. Also, let me know if you think other companies will follow Tesla in making anything like the Cybertruck. Can they? Do they stand a chance if they don't? And are you as excited for Cybertruck as I am? Let me know below. I read all your comments. If you liked this video, please give it a thumbs up to help with the YouTube algorithm, and consider sharing it on social media to help get more reach. Also, consider supporting me on Patreon for as low as $1 a month. It'll really help me invest more time so I can deliver quality content faster. So if you want to support the channel and get access to my exclusive patron-only newsletter, you can head over to patreon.com, and together we can make this channel grow. A huge shout out to my latest patrons, Electric Pioneer, David Finwick, Martin Schinker, and Michael Knoyer. And to all my patrons, you guys rock. You can follow me on Twitter, where I am Connecting No Dots. And until next time, I am connecting the dots, and you are amazing.